but it can't be 0. Why? Because I know that there is some normal velocity of the cylinder. Here is the normal velocity of the cylinder from the motion of the plate. So I get the normal velocity in terms of Q and equate it to the normal velocity in terms of the motion. Okay? This is the philosophy. But the issue is that I goes to 0. Yes, on the cylinder I goes to 0, and if everything else is okay, this means that this guy goes to 0 everywhere. Remember, this is what? This is the radial velocity at the point r and theta due to the pair at phi. So yeah, it will go 0 everywhere except if r also is 0, right? Because if r is 0, then you don't have the numerator only 0, and numerator and denominator. So it's 0 over 0. It's not 0. You need to do, L'Hopital or something to get the next step. R actually will be 0 when theta equals to phi. So you have the entire cylinder here, and you have a point here. So the radial velocity at any point on the cylinder this point should feel the effect of all the source distribution. The radial velocity at that point should feel the effect of all the distribution. It turns out that this effect is 0 except at a particular phi when phi equals to theta. So except, just close, remember this angle, just reminding you, this angle is theta, and we had, this is our Q here, this angle is phi. So when phi is different from theta, so r, large R is not 0, but I is 0, you got 0. So the effect of any source distribution on the radial velocity at this point is 0. But when these angles come close together, they close to 0, then you have an effect. So this means that we need to do it a little bit more carefully. So first of all, this guy was like this. Just to remind you, first of all, this guy was integration from 0 to pi, right? I was integrating over the whole domain. So now I'll do it like this. So V R goes to b over 2, and theta is only the integral from, I'm integrating over phi. Phi is supposed to range from 0 to pi, but all the effects vanish except around theta. Theta minus epsilon, theta plus epsilon. Okay? Any question about that? So you have Q of phi, b squared over 4 sine phi times I over pi r squared plus I squared. Any question, please? Any question? Now we have your limit as r goes to b over 2. That's fine. So let's get things constant outside of the integration. Remember, I is function of theta only, so I can get it outside of the integration sign. That's fine. R is not. R is function of phi and theta. So I will write R as A minus RB cosine phi. Okay. So we have VR at R goes to B over 2, and theta is equal to the limit. Let's get the constants outside. B squared over 4 pi. We can get the I outside. So here's I. the integration from theta minus epsilon to theta plus epsilon. So I'm integrating over this very small range around the angle theta. We have here sine phi d phi divided by so I'll do like this r a so I divided by I squared, so I have I squared down here. I got this I squared outside. Anything missing? This is still I need to put Q. Any questions so far? Just rearranging terms. This R I called it A plus something times cosine, and I divided by this I squared. One thing here to continue the trick, it's not that trick, but one thing here, because we are now here focusing on this very small range, over this very small range, infinitesimal range, the strength of Q is almost constant. It cannot change significantly within this range if it's continuous. So by continuity argument, I can get it outside of the integration. This is Q at theta, Q of theta. It was inside Q of phi, and phi ranges something little before theta, something little after theta. So over this very small range, Q is constant and is almost equal to the value at theta, here outside Q of theta. Now this is an integral of phi. I can compute it. You just give it to Mathematica, will give it to you. I'll give you the result, okay? Because otherwise Q was inside. You cannot do that unless you know the distribution of Q itself, which is unknown. So luckily we have this now. I can do change of variables to make this integral extremely easy. So I'll call, all this guy, I'll call it any variable, chi for example. So I'll call chi to be RB in negative cosine phi over I. So maybe with the A as well, everything inside. So this is all, I will call it chi. So this guy, I will call it chi. So d chi is RB sine phi over I d phi, right? Okay. So, and what else? Remember here you have I with I squared. So I'll multiply here with RB and divide here outside with RB, and now you have this guy. This is actually d chi. So the integral will be the limits r goes to b over 2, b squared over rb pi, q of theta, integration theta minus epsilon, theta plus epsilon, d chi over 1 plus chi squared. This is a very easy integral. Anybody remembers the integral of 1 plus x squared? Remember? Tan inverse. So this is tan inverse. I am between limits. Okay. I can carry out the limit here because this is easy. So this is equal to, if this is b over 2, so I have b squared over 2, goes away. So I have q of theta over 2 pi. Limit r goes to b over 2. You will need to do these kind of tricks. If you have any questions, stop me. So I have tan inverse, okay? Tan inverse chi. What chi is this one? So is here. I'll do it. What is A? R squared plus B squared over 4. So this is almost R squared. We can carry out the limit here, so it's B squared over 2 cosine theta minus cosine phi over I between limits phi equals theta minus epsilon, phi equals theta plus epsilon. I just substituted for chi, okay? Just substitute for chi, and whenever I have r, I put it b over 2 where it doesn't hurt. The only place where I will hurt, the only place where r will hurt if you substitute is I, because it goes to 0. Any other place you can substitute fine. So I have q over theta over 2 pi, and I'm almost done. Now